So we're gonna, okay, going back. I'm just drawing the picture. So we're gonna do this. We'll make it, ooh, that's cool. Thick. It's a thick shell. All right. Cool. And I'm gonna make it, no, that's probably good. Okay. I kind of need the shell to be thicker. Hang on. Here's a hack. Huzzah! All right. This shell is now thick enough. Okay. So in the middle of the shell, we have two. It's negative. It's negative, right? So we have a no, it's negative. Negative. We have this thing, which is negative 2Q. And on the shell, we have Q. Okay? We also have some radii to deal with. So this is, let me just, hang on, I want it to be prettier. So here's R1. And here is R2. Okay? And so we're going to, so this is all, which equation are we using? What kind of problem is this? Gauss. Okay. So this is Gauss's law, which means everything we do should start with, I'm going to draw that better. This is a surface integral. Two wrangled snakes of E dot D. That's actually a great way of thinking of it. Q enclosed over epsilon naught. Okay, so that looks complicated, but when we break it down, it'll get less complicated, hopefully. There are three regions that they want us to deal with. And by they, I mean me, because I wrote this question. How dare they? So we are going to go through all three. And just remember, this is a sphere. We're just looking at a cross section. So all of your geometry should be spherical. As I draw circles, think spheres. It's just much harder to draw this as a sphere because I am not an artist. I am a physics professor.
So the white area is negative space, right?
The white area is just empty space. Yeah, but in reality, you wouldn't even be able to see this charge because it's a closed spherical shell. This is inside of the cantaloupe, okay? So we have three regions. We have R is less than R1, right? We have R is between R1 and R2, which is somewhere in here, right? And then we have R, I'm going to put this over here. R is greater than R2. And let me just make these colorful. So here is, this will be green, and this will be blue, and this will be purple. Okay? And to match that, we'll start with green. So green is anything in this region. Okay? So what we're creating is a Gaussian surface. And remember, a Gaussian surface has to be what kind of shape? Enclosed. It has to be totally enclosed. It has to be a three-dimensional shape. Okay? So this circle represents, what does it represent? A sphere. So that's actually a sphere, with radius little r. And why is it radius little r? Because it could actually be bigger or smaller. It can go anywhere from zero, which is in the middle, to the edge of this thing, okay? So this one we start with, but before we even do Gauss's law, what should the answer look like? What's Q enclosed here?
-2.
Just the charge, right? It's inside the shell, but when we do Gauss's law, we only care about the thing inside the fake thing that we drew, okay? This shell has charge spread out over it, but it's on the outside of what we care about. Since we drew our Gaussian surface, so just to be clear, when we do Gauss's law, there are real things and there are imaginary things. The real things are the shell and the charges, okay? The imaginary thing is the shape you're drawing to make math nice. Because you can draw any shape you want, but only this shape will make things happy, okay? So we know when we find Gauss's law inside of this shell, it has to be a point charge. So that means we know the answer before we even get started is going to be negative k 2q, the negative I just pulled out, over r squared. We know that's the answer, okay? But I'll show you how we get it with Gauss's law also. So with Gauss's law, and I'm going to have to move some stuff, but you do this, E dot dA equals Q enclosed over epsilon naught. And this part we kind of gloss over eventually, but it's worth going over at least once. So because the electric field for this thing looks something like this, right? That means at every point on the surface, we have an electric field vector that points this way. And we also have a surface area vector that points this way. There's a negative here. We're not going to worry so much about that, but they're parallel-ish or anti-parallel. What does that mean for our dot product?
Canceling out.
The dot product goes to, if you say EDA cosine theta, your cosine theta is 1. So you can get rid of the dot product, okay? This is very important conceptually. You can skip over it once you feel comfortable enough explaining it, okay? So that means we can get rid of the dot product. Also, everywhere on the sphere, because it's the same radius, right? Because it's a point charge, so it's everywhere on the sphere, the electric field should be the same, right? Because it's always at the same radius. If you shift the sphere slightly to the left or right, that doesn't work anymore. That's why you have to center it on the point charge. Because if you move this sphere over here, now the radii are all different and the electric field's different at every point on the sphere, and that is bad. Don't do that. I mean, it still works. It just, you'd need a computer to do the math for you. So because we centered it and because we know the electric field is everywhere on the surface of this sphere the same, we can pull out E, we can get rid of the dot product, and we can do this cool thing where we know if you just take the surface integral of a shape, and that's it, there's no dot product left, it's just the area of that shape. And what is the area of a sphere?
4/3 pi r.
That is the volume.
Oh, 4 pi r.
4 pi r squared. So E times 4 pi, and which r is this? Little r, because it's variable. It can be anywhere from 0 to r1. Little r squared. And then Q enclosed, negative 2Q over epsilon naught. Okay, now we just rearrange things, and you end up with E 1 over 4 pi epsilon naught, negative 2Q over r squared, and of course this can be k, so this is k q 2 negative over r squared, which is what we said we were going to get. Okay, so we're not going to do that again necessarily. Let me just move stuff around because we're gonna need a lot of space for this next part. So this part's great. We're going to make it small and move it over here where we don't need it. Maybe over here. Oh, this is a mess. Okay, hang on. Let me rearrange things. Technology. This is so much better than a chalkboard. I just love it. Okay. Oh, and then we're also going to do this one just because it's also easy. Okay. And we're going to skip all the extras and just skip straight to the good part. Because we're putting this Gaussian surface out here. Okay. And it has to be centered, so I'm going to center it. It's kind of centered. Can't really see. Okay. That looks like that. So it can be anywhere from here all the way out to infinity. That's what R greater than R2 means. Okay, so that means this is our little r in this case. And we're reusing little r, but don't get freaked out by it. Okay, we know this is going to look like a point charge where this is negative. Oh, well, this is KQ. What's Q in this case? What's the total charge enclosed? So we have negative 2Q and Q. Q. Negative Q. Negative KQ over R squared. That's it. Actually, we're done. That's all we're going to write about that. Okay? You don't have to go through Gauss's law if you know that's the case. So now we know what it is for inside. We know what it is for outside. Okay? Now we have to do the less pleasant part where we figure out what it is for this guy. I don't know what's happening over there, but I hope it's happy yelling and not sad yelling. Okay. Ooh. Okay. So here's our in-between one, which is, fun times. So that's R. Okay? The left side looks pretty much the same. So if we go to our Gauss's law equation and we say E dot dA is equal to Q enclosed over epsilon naught. The E dot dA part, you'll notice for all three cases, it just looks like E times 4 pi R squared. In this case, R has a different range, but it's still a variable R, okay? Because this side, the A side, is always going to be the Gaussian surface, okay? Where it gets gnarly is at this Q enclosed. Okay? So what's Q enclosed here?
Rho times volume.
Well, it's a little more complicated than that. It's here, let me actually just erase that one. So you also have to include the negative 2Q. So let's say 1 over epsilon naught, we'll just pull that out. That's negative 2Q plus, ooh, this got ugly. Everything, oh, it's not going to highlight. It's doing the thing again. All right. Everything in here. Okay? So that's the Q enclosed there. How do we find out what that is with the stuff we've been given? Just a crap load of spheres. Okay? So what you want is this Q enclosed, but the way you write it is you have a big Q, and then you have volume enclosed. So rho. Let's just start with rho, because rho is nice.
Is this all Q enclosed?
Yes. Yeah. This is all Q enclosed. Okay, but what's rho?
Is the density?
Rho is the density. How do we get the density? It's charge, which is Q, divided by the total volume. Okay, so let me rewrite that. 1 over epsilon naught. Negative 2Q. Do not forget the negative 2Q. It's very important. Minus rho, which we can write as Q over V total, which is the gray thing, times V enclosed, which is the blue thing, and that's that. So let's talk about what those volumes are, okay? And this is where it gets a little bit ugly. So we know that V enclosed, well, let's start with V total. All right, what's V total? What's the volume of the gray thing?
Outer minus inner.
Outer volumes of the sphere minus the inner volume of the sphere. So basically a ball minus a ball. Okay, sphere minus sphere. So that's 4/3 pi R2, the big one, cubed, minus 4/3 pi R1 cubed. Okay, what's V enclosed? That's this area, right? It's the same, but what's different about, which one's different? R2 is now little r, variable r, because as you change r to get it bigger, you enclose, your volume should get bigger until it reaches R2, okay? So that's 4/3 pi little r cubed minus 4/3 pi R1 cubed, because you still have to scoop out the middle, okay? You can write this nicer, but that's the general idea. Okay, because you can rewrite this as 4/3 pi R2 cubed minus R1 cubed. That's ugly. Okay, and this could be written as 4/3 pi R cubed minus R1 cubed. Okay. There's somebody whimpering over there.
I'm just picturing the small r going like, R.
Oh, yes. That's okay. Good. Thank you for that. Okay. Small whimpering R. So it look like this is nice. It looks like it makes sense, but just to be clear, this is V enclosed, and oh no, that's the wrong one. I keep tapping the wrong thing, and this is V total. Okay. So when you plug these back in,
Oh, the 4/3 cancel out.
Yeah, there's some things that cancel. So that's nice. That's 1 over epsilon naught. Don't forget the negative 2q. You can also do this and add it back in later, but I would definitely forget it personally. So, ugh. Oh, this should be a plus, sorry. Plus q, and this becomes this really interesting fraction. So 4/3 pi r2q, oh, this should be little r, sorry. R cubed minus R1 cubed divided by 4/3 pi R2 cubed minus R1 cubed. And so let's cancel some stuff because that's fun. That's satisfying, right? And then, yeah, that's all we can cancel. It was a little bit satisfying. So then we get E is equal to 1 over 4 pi epsilon naught, which is K, right? And then all of this stuff, negative 2q, oh, there's an R, 1 over R squared here. Sorry, that's gnarly. Plus q, R cubed minus R1 cubed over R2 cubed minus R1 cubed. Okay? The important thing here is this is essentially, like, if you look at this term, this is still the term from here, right? It's the same thing. And then what do you expect this other term to look like? Well, it's got this minus thing, but really you're taking an R cubed divided by an R squared. What does that give you?
R1.
Just R, right? Just R, which means it's linear. Which if you watched the Gauss's law videos, anytime you're inside of a shape, you get a linear relationship because as you make your Gaussian sphere bigger, it encloses more and more of the charge. So that means your electric field gets a little bit bigger as you enclose more charge. So that is the answer, and I apologize for the overall hideousness of it, but that's what you would write down.
So this is a test question.
Yeah, this was a test question for a previous class. So, yeah, that's, well, as you can see, you can if I went through this first one a lot slower than you need to. You could actually just write, oh, I know this is a point charge, negative K2Q over R squared, and you don't have to explain that at all. On this one, you could write that just like that, and you don't have to explain that at all. You would still have to go through all of this stuff. But reasonable.
So for what you're saying, like we just explained it, that was the whole concept of it'll always equal Q over epsilon naught, right?
Mm-hmm. And honestly, if you're on a test and you are like, I don't know how to do the geometry here, you could say, well, it should be like the inner point charge plus something linear, and you would get like a 7 or an 8 for knowing that. Yeah, the concept is important. So that's, yeah, does anybody have any questions about that? The other thing you want to remember is conductors behave completely differently. And so there are conductor problems in the homework and in the lectures. So the Gauss's law problem on the test I don't know if it'll be a conductor or an insulator because I haven't written the test yet. I'll write it over spring break. But I'm just as a reminder, we have one integral problem, one Gauss's law problem, which can be a conductor, insulator, or a combination of conductors and insulators, and then one energy conservation problem, which will be my concession to you not going completely insane over the 3 hours. Okay? Any other questions?
Is the cantaloupe a good insulator?